Right, now shifting gears towards equations, we'll start off from the postulate and the first equation and derivation that would follow after this would be from kinetic gas equation, which is PV equals to 1/3 of mNu squared, where P would be pressure of collisions of molecules with container, because we know that there's an elastic collision and there is no intermolecular forces between molecules. So the only pressure that is possible is because of the pressure of collision of molecules with container. As per the postulate, V is volume of container. Again, since the volume of gas is negligible, which is zero, which is not exactly zero, but we consider it zero. That's what we would consider whenever we are using this equation. Then volume of container in our numericals and pressure of collision. M is obviously mass of one molecule, N is number of molecules, and URMS would be root mean square velocity of all the molecules that is present inside the container. URMS would be root mean square velocity of all the molecules. Why all the molecules? Because again, we're considering the volume to be negligible, but there are infinite number of molecules present inside the container. Infinite number of hydrogen molecules, infinite number of helium molecules. So if we want to take into consideration all the molecules, then URMS is basically root mean square sum of all n molecules inside the container. Now, segueing into or transitioning into other equation that is relevant in kinetic theory of gases, which would be required to derive other equations in kinetic theory of gases, we would first try to compute, or we will just compute kinetic energy of molecules. So another heading would be kinetic energy, where Ke, as we know of, is 1/2 mass times velocity of one molecule. Then kinetic energy of n molecules, it would be 1/2 m u1 squared plus m u2 squared plus 1/2 m u subscript 3 squared dash m n u n squared. Right? Now we know that 1/2 times m is common in each of them, so we can just take it out, and what we will have left on the right hand side would be 1/2 plus u1 squared plus u2 squared plus u of n squared. After seeing this equation, you should know, or you should get an idea. If not, then it's alright. You should get an idea that this equation is somewhat similar to what we did in root mean squared velocity. And if we, which is the square root of entire thing, if you are confused. So if we just make some changes in this equation, then we can get something similar to what we have over here in root mean squared velocity equation. So the goal is to get to that point. So with, if I multiply it by n and divide it by n, then what we would have is URMS squared times n, which is kinetic energy of n molecules. Kinetic energy of n molecules. This would be our equations 2, and the equation above here, pardon, is equation 1. Now, computing, let me change the color. And if we divide equation 1 and equation 2, then what we get, or equation 2 and equation 1, is kinetic energy is equals to 1/2 UN RMS squared by PV by 1/3 of M and URMS squared. There's lots of things getting cancelled in this equation, so we cancel those things and we get this equation of kinetic energy is equals to 3/2 times pressure times volume of the container. Now, we know that, again, we know PV is equals to nRT. For 1 mole of gas, it will be PV equals to RT, which means for 1 mole of kinetic energy, would be 3/2 R times T. Why this equation is relevant is it's because it doesn't depend upon the nature of the gas. As per the postulate, where if you think back about the postulate, it explicitly mentioned that kinetic energy only depends on temperature, absolute temperature of the gas. Why this is much more relevant and much more useful in our scenario is because this implies that kinetic energy of any molecule of any gas is independent of the nature of the gas. So there might be a mixture of gases in a container, and all of them having different nature of gases, but whenever we are computing the kinetic energy of that gas, we don't even have to consider, we don't even have to think about the nature of gases, because kinetic energy is independent of everything. And we can just compute the kinetic energy of that entire vessel or gases in it just by using the absolute temperature of that container, which is given by the equation 3/2 RT, which is a big deal in itself. And I'm reiterating the fact that kinetic energy of 1 mole of any ideal gas is 3/2 RT, where again R would be 8.314 joules per mole Kelvin. If we continue this equation from this point onwards, then for n moles, let me change the color. For n moles, the kinetic energy would be 3/2 RT times n. Remember, we are talking in terms of moles here. Moles, not molecules at this point of time. Now, for 1 molecule, since we know about n molecules from unitary method, would be 3/2 nRT divided by Na. And since the number of molecules for 1 mole, for here, is 3 by 2 times 1 times RT, which will be Na, which is required kinetic energy of 1 molecule, which is read as 3 by 2 RT by Na. And if you have heard of Boltzmann constant also comes from here, which would be 3 by 2 kT, where K is equals to nR by Na, which is Boltzmann constant. What's the value of K? K is equals to 1.38 into 10 to the power minus 23 joules per Kelvin. And A would be number of molecule. Avogadro's number. So this has been a bit of a mouthful, and I hope that it's clear that kinetic energy of 1 molecule, kinetic energy of n moles, kinetic energy of 1 mole, and the relationship between kinetic energy and pressure and volume and moles is given. Now, before we solve numericals, what we have to know is whatever equations we have derived to this point, it's not valid for everything. It is just valid for monoatomic gases. What monoatomic gases means is these equations are applicable for gases like helium, neon, boron, argon. It is not applicable in diatomic gases. Like hydrogen, nitrogen, oxygen. However, most of the cases while we are solving numericals in the book, we just strip away the assumption that it is diatomic gas or other gases, but we just assume for the fact that all the gases are monoatomic gases and we use these equations. However, in some cases that might not be the case because there has to be some changes in the equation itself for diatomic gases, for hydrogen, nitrogen, oxygen. But if you solve numericals, then if you read the question carefully, then in most of the cases it should be explicitly mentioned that the question asks you to compute for given there's monoatomic gas in play. Say it would ask you to compute for helium, neon, or argon gases. If it asks for diatomic gas, in most of the cases these equations might not be applicable, but given in our syllabus and university level syllabus for bachelors, you can use the equation, but however, sometimes if you're solving the problems, then it might not be valid. And just to make sure that we are on the same page, you should know that the reason it might not be valid is because of the diatomic nature of those gases. Now, in the other video, we will jump into solving some numericals for these problems, and until then, I'll see you.